In this video, we're going to look at a confidence interval for a mean. So that's going to be when we have one quantitative variable. Just as with the hypothesis test, we're going to do this when sigma, the population standard deviation, is unknown. So when we do a confidence interval, there are generally four things that we're looking for when you do a confidence interval. The first thing is to identify what our population parameter is. So we're going to do that for our example. The second step is to list the conditions, which I have listed here, and as you will see are on your formula sheet as well. We need to still have our random sample of the population, so the idea of being unbiased here. We need to either have a normal population or have a sample of at least 30. And just as with the hypothesis test, I'm putting that the population standard deviation is unknown. But just as when we did the hypothesis test, our sample standard deviation will be known. And because of this third condition, maybe why we're going to see the t distribution show up here. So if I look at this confidence interval, let's pull up the one that we did for a categorical variable for comparison. So on our formula sheet, this was what our confidence interval looked like down here. P hat was our sample proportion. Here we have y bar, which is our sample mean. So again, mean is for a quantitative variable, proportion is for a categorical variable. So that's why that is different. Here we have a z show up, and instead here we're going to have a t show up because of that population standard deviation being unknown. Here when we have s over the square root of n, that's our estimated standard deviation of y bar. For our confidence interval for a categorical variable, this whole square root was the estimated standard deviation for p hat. So it is following a similar format, even though I know the formula itself looks quite different. But now let's pay more attention to our formula here. So y bar, s, and n. All three of those things come from our sample because they are the sample mean, the sample standard deviation, and the sample size. So once we have collected our data, we will have those values. T is very similar to z. If you remember how we found z, it was based upon how confident we wanted to be. So if we were 95% confident, we used one z value, versus if we were 99% confident, we used a different z value. So very similarly here, t is going to be based upon our confidence. So to find t, there's actually two different things that we need. Just as with our z, I need my confidence. The other thing that I'm going to need for a t was that degrees of freedom that we talked about here. For this one, our degrees of freedom is going to be our sample size minus 1. So now that we're working with t, our value is going to be coming from a different chart than the one we had before. So if I pull up my t table for intervals, this is what it looks like. What I see here is that level of confidence. So if I want to be 95% confident, I would just go to the 95% column. Then that degrees of freedom I mentioned is whatever row that we're going to go to. So if I have 20 degrees of freedom, I will choose the 20 row. And then where those things match up will be my t value that I will use. As you go down further in the table, a couple of things to note. The first one is that you notice degrees of freedom counts by 1 for a while, and then it starts changing how it's counting. So there is a chance you could get a value that's not here on the table. So for example, let's suppose I needed to find a 43. 43 is not on my table. When it comes to grading, I'm generally not picky if students use the 40 or the 45 because you arrived in the right place. However, if you want a rule of thumb, or what I do, I always have a tendency to go to the lower degrees of freedom. The reasoning behind that is because since degrees of freedom is based upon our sample size, I'd rather say I had a smaller sample than I did than to say I had a larger sample than I did. So if I go down to 40, I'd be pretending I only had 41 people in my sample. But if I jumped up to 45, I'd be pretending that I had 46 people. So I'd rather pretend it was smaller instead of larger. So if I go back here, let's just go ahead and label that as well. So how confident we want to be just tells us which column we're going to go to in the table. And the degrees of freedom tells us which row we're going to go to in the table. Right, from here we will actually go ahead and dive in and do an example. So let's read through our example. A company is interested in estimating the annual mean out-of-pocket employee health expenses for their employees. They take a random sample of 66 employees. So that's going to tell me then that my sample size will be 66. And found the mean out-of-pocket employee expense for the year was $1,752. Okay, that's coming from just those 66 employees. So that's going to be our sample mean of Y bar with a standard deviation of $1,186. Again, that's coming from just our sample of 66, so it's a sample standard deviation. Our goal is to create a 95% confidence interval for our parameter of interest. Right, so step 1 will be to identify our parameter in words. So mu for a quantitative variable. This here will represent the population mean out of pocket employee health expenses for this company. So that's just what we're trying to find. Our second step is to do our conditions. So again, listing them first, which again are on your formula sheet for you. Right, so looking at how I took my sample, it just said they took a random sample of 66 employees. Again, from what I know, there's nothing bad there. Right, our second condition, we either need to know it's normal. So I don't see here anything in the problem that tells me it's normal. I could also have like a histogram to look at to see if it looked symmetric and unimodal or normal, but I don't have a histogram here to look at. So then I need to have my sample be at least 30. So how big was my sample? Well, we sampled 66 people. So that's big enough. Our population standard deviation, we didn't label it, so it is unknown. But we do have our sample standard deviation of 1,186. Right, our third step is to actually do our calculation. So looking back at my formula, let's look at what we already know. We have Y bar labeled, we have S labeled, and we have N labeled. So before I can use my formula, the only thing I need to find is T, which is based upon my confidence level, and then my degrees of freedom, which is my sample size minus 1. So let's figure out our T. So my row, my degrees of freedom, so 66 minus 1 will be 65. The column is based upon how confident we are. So it told us to be 95% confident. So I'm going to take those two numbers here to my table. So here's our 95% confident. Then I want to scroll down to find my 65. And again, notice I don't have a 65 here. Using my rule, I'm going to round down to 60, which would give me a t of 2.000. So that will be the t that I'm going to use. Now I do have everything to plug in to my formula. So I'm going to take my 1,752, which was my y bar, minus my t, times my s over the square root of n. And then for my upper, same sample mean, just a plus sign now, RT times our s over the square root of n. Now it's just a matter of doing our order of operations correctly. So I'm going to do what's in parentheses here first. And I found that number to be 145.987. So it's going to be the same here on the other side. That number isn't going to suddenly change. Then we got to do our multiplication. And then finally, our subtraction and addition. Here I just rounded to 2 decimals since we were talking about dollars is going to be our units here. All right, and finally then, before we actually do the interpretation, I want to talk about a couple of terms that we've seen before. So if I look at this 145.987, this is what we referred to as the standard error. Versus this 291.97 is what we refer to as the margin of error. All right, so finally we can interpret our interval. So we start with how confident we are. So I am going to be 95% confident. That, and then I'm going back to my step 1. The population mean out of pocket employee health expenses for this company are between, and then finally my numbers. My $1,460.03 and our $2,043.97. Now, a careful word to make sure is here, because it's actually pretty important, is that we need to have this word mean. All right, so this mean here is going to be an important word, because I want to talk about that for a moment here. I am talking about the mean out-of-pocket employee expenses here. I'm not talking about individual people's health expenses. This is the mean. So that's a very important thing to note here, is that this is about the mean. not the individual. If I wanted to know something about individual employee health expenses, that's where like Chebyshev's rule would be important. So that's what I could do if I was really interested in individuals. And thinking outside of a different context here, if I said, that I was 95% confident that the mean exam score is going to be between a 70 and 80%, that does not mean I think that 95% of students will score between a 70 and an 80%. Right, that's where I think the mean of all of your scores will be, not individual student scores. So that's why that word mean is important to us. A question for you to see what you remember. So this interval here is kind of wide. 1,460 to over 2,040. So we're about almost a $600 width of an interval. It's pretty wide. So how could I make this interval narrower? There were two different ways I could do that. One way I could do would be to increase my sample size, because this number here would get bigger, making my standard error smaller, making my margin of error smaller, so my interval would be narrower. The other thing that I can control is to change my confidence, but this is usually where students forget which way. What I would really want to do to make it narrower is I would have to decrease my confidence. So up here where we had the 95% confident, if I changed it to 90% confident, that would make me move over to the next column from where I was. So notice my t would be smaller. So then again, my margin of error will turn out to be smaller if I make this number smaller as well. So on that note, in the next video, we're going to talk about then how big of a sample size do I really need. But before we end the video, it's nice to be able to verify these numbers in StatCrunch. So let's actually show you, even though we did all this math by hand, how can you do it in StatCrunch? I'm going to go to the same place I was in the last video. So we're going to go to Stat, T Statistics, one sample with summary. I'm going to enter in all those sample values that I had. So the 1,752, the 1,186, and my sample size of 66. But this time I'm going to click that confidence interval button. I can change this level based upon what my confidence level would be, but mine is 95%, so I'm going to leave that as 0.95 and hit compute. So if I look at this output, let's talk about some numbers that we can check. One of the first numbers I can check here is the standard error, this 145.987-ish number. Where I saw that was right here. That was my standard error that I calculated when I did the entire formula. Also it gives me my degrees of freedom, which was just our sample size minus 1. And then this L limit is the lower limit of my confidence interval, and the U limit is the upper limit. So they got 1,460.44 to 2,043.56. My numbers are a tad bit different. Now, why did they turn out to be different? Keep in mind that when I went to the table, I was between two different degrees of freedom, and so I had to round in a sense here where StatCrunch is not having to round. So it is nice that when you're doing this by hand, which you are expected to be able to do, that you can use StatCrunch to make sure that you did your math correctly. But as I mentioned in the next video, we will talk about how big of a sample size do we need.